Okay, this will be a pretty rough recording. I'm just doing it seat of the pants, but what I have here is a calculation using GeoGebra, Geogebra. You can get it from geogebra.org, and it's a free download. The version I'm using here is Classic version 5. And so if you want to get a copy and get a copy of this file that I'm using, and you can play with it yourself. But this is basically carrying on a conversation that somehow doesn't go away. And it's the idea that the CIT group is claiming that the flight that came into the Pentagon did not hit the Pentagon, but flew over. And so the flight, in order for it to appear to have hit, it would have to fly over the hole in the Pentagon. And they're claiming that it went north of the Citgo gas station, which is right here. In fact, that's labeled. All right. Right here are all these light poles. It looks like they're trying to basically say it came in a suspicious direction that could not have done any of the damage. The external damage, the internal damage is all lined up along this path here, which is the path endorsed by the NTSB. And it's the path that agrees with the flight data recorder. It's the path of all the damage. And so there's a lot of evidence that contributes to this being the path of the incoming plane that actually hit the Pentagon and plowed through the outer three rings here. Okay, so the idea is if they could show that it came around this way, then what they've got is proof that all of this damage was faked. Okay, my take on that is it's absolutely, totally implausible to fake all of that damage. The amount of damage they're talking about is overwhelming. However, let's just take their flight path and look at it for plausibility. This is something that Frank Legg and I did back in 2011. We published 2 papers on it. One was on the website for Scholars for 9/11 Truth and Justice, and then there's a second one that was a follow-up to that in a different website. Okay, let's take a little break and look at some background physics so you understand what's happening behind the scenes, what GeoGebra is calculating. Okay, the idea is this: if you have an object that is moving in a circle, it's going to take a sideways force to make it move in a circle. The reason for that is Newton's first law of motion is that an object, if there are no forces acting, it's going to tend to move in a straight line at a constant speed. If I apply a force to it in the forward direction, it'll cause it to speed up. If I apply a force in the backward direction, it'll tend to make it slow down. If I apply a force sideways, like this, then it's going to cause it to curve. So you can think of it as the little change in velocity is this direction. And so it started off going this way, and now it's going this way, all right? Now, this force has to be purely perpendicular, and that's easy to understand if you think about it a minute, because if there were any component of that force that were in the forward direction, it would cause this thing to speed up. And if any component was in the backward direction, it would tend to slow it down. So in order to curve the path so that it's flying at a constant speed but in a curved path, the force has to be purely perpendicular. And if it's in a circular path, it's the same curvature everywhere, so this force is going to be a constant. So this force, which is pointing toward the center of the circle, is called the centripetal force. So that's the force toward the center. Now, how much force is involved? Well, that depends on how much mass we have here, and it depends on the speed, and it depends on the radius of curvature. And the relationship, it works out if I'm not going to do all the derivation here, but it turns out to be mass times velocity squared divided by r. And that's going to give you your centripetal force. That's a C there. Okay. So The centripetal force, the force needed to bend the path into a circular arc, depends on the mass of the object, the speed, and the tighter the curve, the smaller the radius, the larger the force has to be. Okay, so making the numerator big makes the force big. Making the denominator small makes the force big. Now, Newton's second law says F equals ma. So all of this that we've been saying about the force can be translated to a simpler comment about the acceleration. This force leads to what's called a centripetal acceleration. And just take the force divided by the mass, and that gives us the acceleration. So if I divide this by the mass, instead of this being a force, that's now centripetal acceleration. And this is what GeoGebra is going to calculate, all right? Let's see how this applies to the banking angle. If this is a plane, in order to fly in a curve, it's the wings that have to provide this centripetal force. So there has to be a sideways component of the lift from the wings in order to pull it into a circle. And in order to get that sideways force, you need to bank the plane. So the wings are partially lifting inward as well as lifting upward. Let's take a look at that. So I'm going to do two pictures here. If here's our plane flying normally, we have gravity acting downward, but what the plane has to provide is lift in this direction. Okay. If it's going to be flying in a circular arc, it has to be tipped. And so now here's the plane. I'm imagining the plane is flying directly away from us, and the lift on the wings is going to be in that direction. Okay, I'm going to draw a slightly larger diagram here. This lift is going to be doing two things simultaneously. It has to provide some upward force because it still has to balance it against gravity, but it's also going to be providing a sideways force in order to cause it to go around in this circular arc. And so if I combine the two, the upward force combined with the sideways force results in something of a net force like this. And if I break it down, we can see a couple of triangles here. And so that's the direction that's going to seem like it's up. If you're in the plane, it's going to feel like you're pushed this way. That's the reaction to this force, but the lift is providing a force over here. Notice that's perpendicular to the wings. It's the wings that have to provide that force in this direction. Okay. Now, we want to calculate the tip of the wings and see how that relates to our acceleration. So let's take this angle here and just call it B. That's going to be our bank angle. That's the angle of our banking. That's the angle of the wings from the horizon. That's also, I think you can see, it's going to be equal to this angle. It's the angle between the tail and vertical. Why is that true? Well, look at this angle in here. B plus that angle adds up to 90 degrees. But this angle plus this angle adds up to 90 degrees as well. Okay, so these have to be equal. So let's look at this triangle. And what do we have? This is the force that's counteracting gravity. So it'll be the force of gravity, and here's your centripetal force. Okay, and so those form a right triangle. And if you know any trigonometry, measuring from this angle down here, that's the opposite side. And this is the adjacent side. This one is called the hypotenuse, okay? And the opposite over the adjacent is the tangent. The tangent of B is going to be F sub C over F sub G. And we saw earlier that if I divide by the mass, I get accelerations instead of forces. I could go either way. But the mass basically is irrelevant. It cancels out. So let's just do that. So that's the same as acceleration centripetally. And this is the acceleration of gravity, which is just called G, by the way. And if you express the centripetal acceleration as so many g's, like let's say, for instance, 3 g's, we now have 3 g's divided by g, cancel, cancel. We have a number we can plug into the calculator and figure out this banking angle. So the tangent of the banking angle, whatever it is, gives us 3. The inverse tangent of 3 would give us the banking angle. So let's look at that. Okay, pardon the fancy calculator. Ignore the top row. Everything's going to be in the bottom row here. So if I put in a 3, and then I say I want to know the angle that's going to give me 3 as its tangent, that's finding the inverse tangent, or ATAN there. So I go orange and hit that. Notice that's going to give you a 71 degree, 71.5 degree roughly. That's going to give you this kind of a banking angle in order to get 3 G's. By the way, just for reference, if you're on a ride at an amusement park that gives you a sustained acceleration of 3 or more G's, you're going to have people that are going to start blacking out. I was on a ride that was something like that, and I started getting black spots in my vision. So this is a lot of G's. The plane is designed to only go 2 point something G's normally, and 3 is probably sustainable. But once you start getting much above that, you're putting the structure of the plane at risk. Okay, bottom line, we're going to be looking at arc curvature, and the arc is determined by the radius, and then we're going to have the velocity, and from those we're going to get the centripetal acceleration, or I'm going to call it lateral accelerations, the sideways acceleration here. And from that, we're going to evaluate paths that give us reasonable values for these. By the way, notice that even if you could survive a 3G bank, you're going to notice, observers on the ground are going to notice a 71 degree banking angle, definitely. That is very, very steep and unusual for a plane. So you're not going to get sideways accelerations that look like this unless you have every observer out there on the ground saying, look at that weird plane doing a huge bank. That was not observed. So big accelerations are unfeasible dynamically. Even accelerations like this are going to give you banking angles that couldn't help but be observed. Okay, let's go back to our primary video now. Anyway, so what I have here is an arc that we can play around with, and I've done a computation based on the curvature of this arc to translate the curvature of the path to what is the lateral acceleration. This is given by v squared over r, and then you have to convert the units to make them come out. Right down here in the left corner is where Ed Pike had his auto repair shop. And he basically testified that the plane came more or less overhead. He was sort of waving his hands around, a little bit hard to say exactly. It was a little bit to the south of him, but in this general area. There are questions, by the way, on whether he was actually outside where he could see it. It seems from later conversations that he was actually inside looking out through a window. So that would put the plane a little bit further south probably. But whatever, we're not going to quibble about that. Let's just put the starting point of this arc down here pretty much at his service station. And let's put the this point up here somewhere and this point here at the where the hole is in the Pentagon. All right. So in order to get the curvature needed to go from Ed Pike's shop to a point north of Sitco, where these other people are saying it flew, and then not hitting, but flying over this hole. The curvature here is indicating a lateral acceleration of up around 5 Gs, 4.5 Gs, and a corresponding banking angle of about 77, 78 degrees. This kind of a banking angle was not observed. All of the observers had it flying. If they had a little bit of inclination to the plane, it was just very slight. Okay, However, if you go back and look at the actual video where Ed Pike does his interview, he actually draws a line that sort of goes like this across the Navy Annex. And so apparently whoever did this compilation of all these paths, I assume it's maybe Craig Ranke or whatever, but they have it so he's going across here. And problem is, if you go in that direction, let's put this back at Ed Pike's place, and let's just go like that direction there. Whoops, we're going south of the Citgo station. So somehow you have to get north of Citgo, and even there you have about a 68-degree banking angle, and 2.5 Gs is way up there for a 757. But there you go. So this would be a high lateral acceleration and a very steep banking angle. This is not typical for flying. It would probably hold together at this angle, I'm guessing, but somebody with more aviation expertise could comment on that. But in any case, let's look at some of these others. If I just take sort of an average of all of these different witnesses and say, all right, let's take a curvature that's something like that. Notice again, we have banking angle 78 degrees. Here's 4.8 Gs. If I basically take the Ed Pike diversion thing here, that's 9 Gs, totally out of the realm of reality. Anyway, the bottom line is you can't just play around with just saying, oh, the plane turned. From Ed Pike's auto shop to the impact or the flyover, whichever you believe it happened, this is 5 seconds, just under 5 seconds. How do you get a plane to divert like that? Now, in the paper that Frank Legg and I did and published back in 2011, the acceleration was even greater, because what we did was we took the plane as coming in along the official path until it diverted. There's the Ed Pike testimony. There's also another person, I forget his name right now, but it was along this edge of the Navy Annex somewhere. There's also Albert Hemphill, who was right about in here on this wing of the Navy Annex. So if you go from it coming in, like Craig Ranke asserts that, oh, he didn't say it was coming in on his right shoulder. It came in over his right shoulder, as though it could go from there to the north of the Citgo somewhere and then over. That's an 80-degree bank angle. Okay, 6 Gs. That's not going to happen. All right, or if we even take it from here. So it's even more extreme if you assume that you have to take from this essentially straight on aiming at the Pentagon flight, which all the radar data indicates, and the flight data recorder both, and a lot of witnesses along this path. But if you take it curving left and then curving right, there's another element that comes in, which is you have to roll in order to get a left bank, a steep left bank like this, and then you have to roll and then get a steep right bank. And you can't roll from way left to way right. Maybe a fighter jet could roll over it in a couple of seconds, but you're not going to get a 757 to do that in under maybe 30 seconds or something. It's going to take a long time to go from a steep left bank to a steep right bank. And that kind of thing. These bank angles just don't happen, by the way. So anyway, bottom line is if you start just looking at it with just even some basic plausibility investigations like this, it looks like any kind of a path that's not going straight into the Pentagon from here, that's going to curve up and over and around. You're not looking at the implications. You're looking at high lateral Gs and high bank angles. These are implausible, and bottom line is the CIT flight path does not represent reality in any way. You can't make it happen.